Hello, students, and welcome to my screencast on atomic review and water for our biochemistry unit. There will be 3 videos. There will be this one about macromolecules, and one about enzymes to help you prepare for the test. And here's some pictures of water that I was just at, Kaloof and Amman and the Chetty. Wonderful places. This is licensed underneath the Common Creative license. So what these pictures mean here is that nobody should profit from this video. It's just meant to help you, and it's free to be shared or used. A lot of the images I get are from Khan Academy and OpenStax, and those are available for free at khanacademy.org and openstax.org. Let's jump in. So what is this video going to go over? Why is water a polar molecule? How does hydrogen bonding work? And due to these emergent properties of hydrogen bonding, what are 4 properties of water that make it vital to life? And can you give some examples of each? So pause the video, try and answer these questions. If you can answer them without consulting the internet or your notes, then you know this material and you can move on. You don't need to watch this. Okay, to understand why water is a polar molecule, we have to review just a little bit of chemistry. All right, and this is beginner chemistry stuff. So think back to an atom, the model of an atom, and what's on the inside and what's on the outside. And so let's look at helium here. Hopefully you got that helium has 2 protons and 2 neutrons on the inside. I can get the number of protons because it matches the atomic number on the periodic table. If you need a periodic table, just Google one and they'll pop up easily, and your iBook also has one as well. How do I figure out the number of neutrons? I just take the atomic mass and subtract the atomic number. And so 4 minus 2 gives you 2 neutrons. You might wonder, why is this atomic mass 4.003? That's because it encapsulates, or it has within it all the different isotopes of helium. Isotopes are helium atoms that have the same number of protons as this, but have a different number of neutrons. And so then the electrons are negligible or don't have a mass. They're very, 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 very light. But we know that there's 2 of them because they have to equal the number of protons. If the electrons don't equal the number of protons, then it's called an ion. Okay, why do atoms bond? Can you pause the video and think about it? So you might remember in class, I kept talking about 8. 8 is great, right? The octet rule. Well, atoms really bond because they want to reach their most stable or lowest energy state. And it's done by filling the valence shell with electrons. So they want to have 8 in their valence shell. And I make this caveat, right? Atoms don't really want something. We can't give them human qualities. I just kind of use that in class to help you learn the material. So look up sodium on the periodic table and make a Bohr model. And try the same with chlorine. All right, if you look them up, you saw that sodium has 11 protons. It's in the 3rd period. By that, I mean the 3rd row. So that means it's going to have 3 energy levels. The first energy level only holds 2 electrons. The second energy level can hold up to 8. So if we look at sodium there, you can see the 8 in the 2nd level. And the 3rd holds 1 because we have 2 plus 8 is 10. And in the 3rd level, we have that 1 leftover one. Now it's going to need 7 more to fill that outer level. Let's look at chlorine. Chlorine is 17. It's still in the 3rd period. So it's going to have 2, and then it'll have 8, and then it'll have 7 on that 3rd level. 2 plus 8 plus 7 is equal to 17, right? 10 plus 7 is 17. So look, this is kind of a match made in heaven. And that's what I just told you about the periods. This is just a repeat of my slides from class. So here's what I was trying to go over. That sodium will lose an electron. It will give it to the chlorine. So when it transfers it, this is called an ion now. So the Na is positively charged. It's like a kitty cat. It goes purr. So it's called a cation. The chlorine is now negatively charged because it's gotten another electron. So it is called an anion. It's not important to remember those. What's important is the concept, right? So Na is positive, chlorine is negative. Well, now they're attracted to each other, just like north and south magnets. And so that's called an ionic bond. So that's one type of bonding. Here's another type. This is called covalent bonding, and it's when they share electrons. And I remember that because CO stands for a couple. So here would be hydrogen sharing electrons with itself. So it's H2 or hydrogen gas. And this is happy, right? They're each happy. Once again, giving it human qualities, sorry. But it's fulfilled the inner energy level. And let's look at water, right? And so water here, the two hydrogens for H2O share their electrons with the oxygen. So let's look at oxygen. 1, 2 in the inner level. 1, 2, 3, 4, 5, 6, 7, 8 in its second energy level. Now, oxygen's good to go, and the hydrogen's good to go because it has 2 in its inner energy level. So they're, in essence, sharing the electrons. So instead of transferring them like in an ionic bond, they're sharing them. So this is covalently bonded together. So what does this mean? Well, due to these properties, water is going to have a charge. And this is just another one from class. Water exists as a solid, liquid, and gas. It's H2O. So using these words, covalent, electrons, hydrogen, oxygen, can you say why water's polar? Let's go ahead and stop the video. All right, hopefully you got something like this. The electrons that are shared will be shared around the oxygen more often. Oxygen is a more electronegative element, and by that we mean that it's stronger. It has 8 protons versus the 1 proton in each hydrogen. So it's going to have the electrons a disproportionate amount of time or more often. So they'll be more often around the oxygen. So this will be slightly negative, and these will be slightly positive. If it looks like an upside down Mickey Mouse, the ears are positive and the face is negative. That's going to give water a slight charge. And we know that negatives and positives attract, so that's going to lead to a new property. So here was my slide from class, right? And so this just shows that you can pause the video and go back over that, or you can look at your notes if you took them. So this is called an emergent property. It's pretty cool. It comes out of having multiple water molecules around. If you only have one, or if you're only talking about the covalent bonds within water, it's not going to have this emergent property of hydrogen bonding. It'd be like on a football team, if you only had one player, right, you couldn't pass the ball around and do formations and other activities that you can with multiple players. Same for basketball. So here, can you explain the emergent property of hydrogen bonding? Well, here you can see the positive hydrogen is attracted to a negative oxygen on another water molecule. We represent this with dashed lines. It's not as strong as the covalent bond within these molecules. We use the water kits in class to help model this. And I told you in liquid water that they're constantly breaking and reforming these hydrogen bonds. So hydrogen bonding is pretty cool. It's also what holds together our DNA, and it's going to give water properties that make it special and then help permit life on Earth. So here are my notes on them. So can you recall the 4 emergent properties of water that help to sustain life on Earth? You probably remember one of them because we did the modeling with dissolving salt, etc. But go ahead and pause the video. So here we go. Here's what I got for you. So I wrote out what an emergent property is. The whole is greater than the sum of the parts. And so there's really 4 things that I tried to go over in class and tried to have you do some little water Olympics with it. B block, I still owe you that. And so the first one being that cohesion, adhesion, right? Water molecules tend to stick to themselves. So here I have my Nalgene of water. If I stick my finger in and then hold it here, you can see some water clumping on it. It's engaging in cohesion between the water molecules and adhesion to my skin. So that gives water some unique properties that it's able to bond to itself. All right. It has a high specific heat. So in this, we talked a lot about cars and radiators. Why do you put water in a radiator? Why do we sweat? It helps to cool us down. Water in density, it's one of the only solids that's less dense than its liquid state. So once it freezes, it's going to freeze from the top of a lake down, or ice floats because it's less dense. And water is called the universal solvent. It can dissolve lots of things. It can't dissolve everything, but it can dissolve lots of items. So the following slides are going to kind of take you through this, and I'm going to do them quickly. And you can review them in Google Classroom. So here, cohesion like a couple, adhesion sticking to a surface. This plays a role in transpiration. So as water escapes through the stomata here in what's called evapotranspiration and goes to an area of lower what's called water potential, or it evaporates, it's going to pull water molecules up the tree. So trees don't use energy to move water all the way up to their tallest leaves. That's pretty cool, right? They just use the properties of water, cohesion and adhesion. It's going to be adhesion to the sides of the xylem cells and cohesion between the molecules. Okay? And so trees can have problems if they get an air bubble in there that's called cavitation, and that can be harmful for the tree. Okay, the thermal properties. So as water evaporates from a surface, it's going to help cool us down. It's going to be the kinetic theory of matter. The temperature is really moving around of molecules. So the ones with the most energy are going to be bouncing off and evaporating to help cool us down. Water also takes longer to heat up than other substances. So if you were to put a pot of oil and a pot of water on your stove at the same time, the oil would heat up quicker. That's kind of deceptive, right? Because oil doesn't boil like water, but it does heat up quicker. So this is good, right? Because lakes and oceans can absorb a large amount of heat and only change a few degrees. If they change really a whole bunch, then it might hurt the life inside of it. It's also good for us because it helps to keep us at a stable body temperature, which is really important for our enzymes to work. Right? Think about it like this. If you have your car hood after you've been driving around for a while, you touch the top of your car hood, it's really hot, but the car on the inside is still working because the water helps to keep it cool. Okay, it expands upon freezing. So once it freezes, these hydrogen bonds keep the water molecules in what's called a lattice structure. So it's going to have more space in between them. And since density is equal to mass divided by volume, if volume in the denominator goes up, then density overall goes down. So water in its solid state of ice is less dense than liquid. Here it is dissolving, so this is important. Here you can see these positive hydrogens are going to be clustered around or forming what's called a hydration shell around the chlorine anion, and here the negative oxygens are all around this positive sodium. So they're pulling apart this ionic substance, right? And so it can pull apart ionic substances and polar substances, things like sugar. It doesn't pull apart the actual sugar molecule, but it pulls apart the clumps of sugar. So it spreads it throughout your tea. All right, but this doesn't work for lipids and other non-polar items. Okay, that's my boy telling you that he hopes you hit a home run with water, and we'll see you in the next video on macromolecules. That one will be slightly longer.